In the previous lecture, we looked at phase coexistence in general. In this one, we're going to zoom in a little bit and look specifically at phase coexistence within liquids. A single component liquid only exhibits a single phase, but if you mix two components together, you can have phase coexistence. Well-known simple examples, if you try to mix water and oil, they don't really mix very well and you will get phase separation, the water and the oil both being in a liquid phase, though in practice there will always be a little bit of oil in the water and a little bit of water in the oil. We also see this in biological systems, for instance in the lipid bilayer, which is also a liquid-like fluid, where the various lipids can phase separate, as we will discuss much more extensively when we talk about membranes. And liquid-liquid phase separation is also known to exist inside cells and is also currently being investigated quite intensely because people think this may be one of the ways that cells compartmentalize themselves even without the use of membranes. For the purposes of this lecture, we're going to look at two components to keep things relatively simple. We'll have particles or polymers or something, some solute that's dissolved in some solvent. Typically particles in water, but it could be anything. And actually these are just labels such that we can indicate the two different types of particles. So we're going to label them with a P and an S. The relevant free energy will be the Helmholtz free energy, which is given by the internal energy minus the temperature times the entropy, the amount of free available energy, which will be our guiding factor throughout this lecture. The Helmholtz free energy in general is a function of the temperature, the volume, and now of the number of particles of the two systems, so of the number of P particles, polymers, particles, whatever, and the number of solvent particles. But of course, these are not completely independent quantities. A particle takes up some volume. Every particle a specific amount of specific volume. And what I can say is that the total volume in a liquid, where there are no gaps between the particles, is the volume per particle times the number of particles. And of course, I have to then sum over the various cases because the solvent particles and the solute particles do not necessarily need to have the same volume. If you want to be really precise, you can define these specific volumes as the derivative of the volume with respect to the number of particles while keeping all other parameters fixed, in this case at constant temperature, pressure, and number of P particles, and of course the other way around. All right. Now, working with number of particles is still not the easiest way of dealing with things, because we are going to mostly look at a closed system where the total number of particles is going to be fixed, the total volume is also going to be fixed, and we're going to change the relative fraction of solute to solvent particles. So the most easy parameter, and that will also be our order parameter, is to define phi as the relative volume fraction of the number of there's a number of solute particles. You can also, of course, take the number of solute particles, doesn't matter, right? So I'm going to define this as VPNP, right? The volume taken up by the solvent particles divided by the total volume, or introducing this, using this expression above, we get this expression. Now, this is then the volume fraction, which will be ranging between 0, in which case we have a single component liquid consisting only of the solvent, consisting only of the solvent, and 1 where we have only the solute, only the P particles, and any ratio in between. Now, working with the total free energy is also not the easiest way of working. It's easier to work with the free energy per unit volume. Right? The free energy is an extensive variable. If I double the size of my system, the volume and the number of particles double, as does the free energy, but it's easier to work with intensive variables. And so I'm going to define the free energy per unit volume through simply taking F equals V times small f. So small f will be my free energy per unit volume. And now my free energy per unit volume, it will no longer be a function of the volume, of course, and it will be a function of the ratio of the number of particles of type P and type S to the total volume. But then if I have found one of them, I can find the other one trivially because the total number of particles is conserved. And therefore, this F will be a function only of the temperature and the volume fraction. In practice, the temperature is not going to be of our main concern here, because if we have a liquid that is at least relatively well mixed, or is equilibrated for long enough, the temperature will be uniform in the liquid. So the two phases will always be at the same temperature. Of course, I can change the temperature globally of the whole system, and then things can change. But our main parameter here will be our order parameter phi, the relative concentration or the relative volume fraction of one of the two components. All right, so now to find an expression for small f, this is free volume the free energy per unit volume, here's a very neat trick. It's a trick that I haven't found in any book, but I can't claim credit for it because I learned it myself from Tom Lubinsky, so I'm sure it is somewhere in one of his many writings. And it's actually quite simple, but it will give you various relations between pressures and chemical potentials and so on that other books use quite extensive calculations to get. So this one is nice and elegant and much faster. So this is the trick. We write not the full form of the free energy, but the differential form, which we get from the first law of thermodynamics. The differential form of the free energy is minus the entropy times the differential of the temperature, minus the pressure times the differential of the volume, plus the chemical potential times the differential of the number of particles. Now we have two types of particles, so we have two chemical potentials, mu p dnp and mu s dns, right? Reflecting the fact that the free energy itself is a function of temperature, volume, and the two numbers of particles. Now, if I rewrite the free energy saying that, well, but this is simply the differential of V times the free energy per unit volume, and differentials obey the product rule, so we have V dF plus F dV. Now I can also do the same thing on the other line. I have the entropy, which is an extensive variable, so it scales with the volume, so I can write it as the entropy per unit volume times the volume itself. So it's minus small s V dt. I have a pressure times the variation in the volume. I'm just going to leave that. And then the number of particles I can find from the volume by scaling it with phi. And to be precise, the NP I already have from the equation up here. NP is phi times V times divided by the specific volume of a particle. The specific volume is a constant, so I can pull that out of the differential. Right? So I have mu p over Vp d phi times V. And for the number of solvent particles, I get the same thing, except that now I don't get phi, but 1 minus phi. So I have plus mu s over the specific volume of a solute particle, d 1 minus phi V. Of course, this is all within the differential. All right, so now I can work this out. This is just some math. Right, again, I have a chain, not a chain rule, a product rule for phi times V and 1 minus phi times V. So we have minus S V dt minus P dV plus mu P over Vp times phi and mu S over Vs times 1 minus phi times dV plus, and now the other terms, mu p over Vp. And now for 1 minus phi, the differential of that is, of course, minus the differential of phi. So it's minus mu s over Vs V d phi. And now if I collect terms, I see that I have some terms that scale with the volume outside the differential and some terms that go with the differential of the volume, but I have nothing else. And also I had this in the top one, right? I have one term here that goes with the volume and one term that goes with the differential of the volume, this one. And so what I can say, well, this differential of the volume, it has no volume before. The differential of the free energy per unit volume has no volume in there anymore. And so I can simply read off what these two things need to be. So instead of one equation, I get two. And what I get is that the free energy itself, so from the second term, so I typically collect all the terms that go with dV. Well, that's minus the pressure. There's one there. And then there's this big thing within brackets, which I'm going to rewrite a little bit as mu phi times phi plus mu s over Vs. Now, of course, I have to do a proper definition, right? Then mu phi is mu p over Vp minus us over Vs, right? So it's the combination of this one and the second one. The last one here is just a constant for the purposes of our discussion today, which we'll see in a bit. And then the other one, the differential of f, which is in some sense even more useful. It's minus the entropy per unit volume times the differential of the temperature, which if I keep the temperature constant is going to be 0, plus, and again I can combine and use this new defined mu phi, this one here, and see that this is plus mu phi d phi. Right, so I have some kind of combined chemical potential, which combines the chemical potential of the two types of particles. And then there's also the remaining chemical potential of the solute itself, but that's not going to be changing anymore. Now from this second line, I can say, well, if the temperature is constant, I see that a small change in the free energy per unit volume can only come due to a small change in this volume fraction. And the ratio of these two is going to be the chemical potential. In the limit of that ratio, of course, this thing becomes a derivative. And so what I have is that the chemical potential of this relative volume fraction is the derivative of the free energy per unit volume with respect to the volume fraction itself. And to be precise, it has to be taken at constant temperature. And from the top line, I can read off that the pressure is then, which usually is the derivative of the free energy with respect to the volume, keeping everything else constant. So in this case, the temperature and the numbers of particles of both types. I can also now write as, well, it's minus the free energy per unit volume itself, plus mu phi times phi, and for mu phi I found the derivative, so it's phi times the derivative of the free energy per unit volume, and now minus, because the p has a minus sign, plus us over Vs. Well, that's simply the free energy when the concentration of particles is 0. Right? So this is plus f at 0. Right? This is going to be a constant that's going to be the baseline of our pressure. Now this is, in a sense, right, this is the pressure due to an excess of particles. This is not the regular pressure, this is the osmotic pressure that we get here. There can, of course, also be a regular pressure that has to do with changes in volume, but because we are talking about a liquid here, changes in, the liquid is to all intents and purposes incompressible, so that sets a baseline pressure, but other than that, it's not going to change anything. What we can change pretty easily is the concentration of the particles, and therefore we are dealing here with the osmotic pressure. Right? So similar to what we had before when we were talking about coexisting liquid and gas phases or things like that, now we have coexisting fluid phases, so coexisting liquid phases that have a newly defined role for the pressure and the chemical potential, which are related to the relative concentration of one type of particles in a solution of the other. All right, so, and for phase coexistence, everything else still holds, right? So phase coexistence requires us to have equal temperature in both phases, and then equal osmotic pressure and equal chemical potentials. So if we want to find concentrations at which we have phase coexistence, we need to find functions such that, or we need to find the points such that these two numbers are equal, again, assuming that the temperature is uniform throughout our liquid. So how do we do that? Before we actually do this on a concrete example, it's nice to see that with the very general argument, we can already say under which conditions we will have phase coexistence and under which conditions that will not happen. And that's because we can simply derive what's known as a mixing criterion. So suppose we do the following thought experiment. We have two beakers with two solutions, one with volume V1 and concentration phi1, and one with, surprise, surprise, concentration phi2 and volume V2, and we put them together. So what do we get? Well, we get a new, if we put them together in some new beaker, of course, the new volume, and we also get a new concentration. Of course, the new volume is very easy. It's V1 plus V2. The new concentration, however, the new volume fraction, which boils down to the same thing, depends on whether this thing actually mixes or not. If it does mix, it's simple algebra, and we can very easily calculate what this thing is. It's the original volume fractions times, but it's the volume fraction of the particles. Well, that's the number of particles we had in beaker 1 plus the number of particles we had in beaker 2 divided by the total new volume. Right? So it's phi1 V1 plus phi2 V2 divided by V1 plus V2, which I can also write as x times phi1 plus 1 minus x times phi2, where x is now the ratio of the volume 1 over the total volume. Now, however, right, that is if everything nicely mixes. When does it mix? Well, it mixes if that lowers the free energy. So that means that the free energy, and I don't mean the total free energy, not the free energy per unit volume, but the total free energy of this new combination is lower than the free energies that we had before. If that's not the case, then they will stay separate. For instance, which is for instance what happens if I had pure water and pure oil. I can put them together in one beaker, but they will stay separate because the free energy will not be lowered by them mixing. So for mixing, what I need is that the total free energy, which is the volume times the free energy per unit volume at this new concentration, needs to be lower than the sum of the free energies that we had before, which is V1 F of phi1 plus V2 F of phi2. Or if I write this in terms of this variable x, which is why we introduced this thing in the first place, it's f of x times phi1 plus 1 minus x times phi2 must be less than x f of phi1, 1 there, plus 1 minus x free energy per unit volume of phi2. All right, and this must be true for any value of x between 0 and 1. If not, if there is a value of x between 0 and 1 for which the right-hand side is lower than the left-hand side, we can demix the system and thereby lower the free energy, and that in general will then also happen. Now, mathematically, what does this mean? Well, actually, it may look daunting if you just see me say jiggling around the algebra, but it's actually quite a simple condition. And the condition is that the curve of f is what's known as convex, meaning essentially that the curve of f has to look something like this. So we have phi and we have f, and the curve of f has to look something like this. We can have a single minimum, and between any 2 points, the line connecting the 2 points is above the curve itself. And so this is known as a convex curve. When this does not hold, this is of course when the curve is not convex, meaning that there is some region in the curve where the line connecting 2 points on the curve is below the curve itself. That's called a concave region. And an example would be something like this, where we have a curve that has a little bump in it. Because then if I look to say the points here and here, I can draw a line between them and it's below the curve, obviously. So this is a concave region. Now, when does a curve become convex or concave? Well, this is a pretty easy question to answer if you know the function. Because a convex curve has a positive second derivative everywhere. A concave curve, at least the concave region, has a negative second derivative. And of course, then there's a point where we switch from one to the other. Right? So a convex curve, a curve is convex if and only if, and that's this condition. That's true if and only if the second derivative of the free energy with respect to the concentration is positive for all phi. Well, here the relevant numbers, of course, are phi needs to be in between the phi 1 and phi 2. But essentially, we want this to be true for all phi's between 0 and 1. All right. The other option, the concave region, here we have that the second derivative of f with respect to phi square is negative. And if we have a concave region anywhere in between the two original concentrations, we will not get a complete mixture. Of course, in general, the numbers will change a bit. Right? There may still be a transfer of, say, oil. Right? If you have water-oil mixtures that we mix together, there may still be transfer from oil from one of the mixtures to the other, such that we get the optimal free energy, but it will not in general mix. So how do we find out what this optimal free energy is? Well, there we go back to the physics conditions and we say, so we could prove this mathematically, but it's much easier to go back to the physics conditions. We say, well, we know that for phase coexistence, we must have the same chemical potential and we must have the same pressure. Right? So we're going to get two concentrations, let's call them phi A and phi B, at which we will have, right, so phase coexistence, right, which we will have that the chemical potential at phi A equals the chemical potential at phi B, which means that, well, the chemical potential is simply the derivative, right, that f prime, right, the derivative of f at phi A equals the derivative of f at phi B, and the pressure at phi A must also equal the pressure at phi B, oh, not FB, which means, well, if we look up what we found for the osmotic pressure, it means that it's the function minus the function itself plus this volume fraction times the derivative of the function, and then of course plus f0, but I mean that's the same for both, so that's not going to show up. So we're going to have minus the free energy per unit volume at phi A plus phi A times the derivative of the free energy at phi A equals f at phi B, minus f at phi B plus phi B times the derivative of f at phi B. Now graphically, we can illustrate this very nicely. The first condition simply says that we need to find 2 points for which the derivatives are the same. Now if we look at this curve, and let me draw the curve again, with this concave region, right, and let me draw it a bit more exaggerated here. Of course, there are many points that have the same derivative. Right? If I look here, there's a downslope, and here there's a downslope. These 2 points have the same derivative. There's an upslope here and an upslope there. These 2 points have the same derivative. They will not be coexisting phases because just having the same chemical potential is not enough. If we look at this condition, here we find that we have, well, what is this? This is the value of the function, well, minus the value of the function, plus phi itself times the derivative. This is an equation for the tangent line. Right? The tangent line to the function, and it needs to be equal to the tangent line of the function later on. Right? So what do we have is we need to find 2 points which have the same tangent line. And so what we can do is take our ruler. I don't know if I can do that here. Yes, I can. Take a ruler and find 2 points where the tangent line to the curve is the same. And then we find that the 2 points at which we're touching here are the values phi A and phi B. So these are not the local minima. They're fairly close, but they are not exactly the local minima. Sometimes you can still transfer particles from one phase to the other, lowering the total free energy without sitting in the local minimum. If the whole curve is symmetric and you have two local minima that are at equal depth, then of course the tangent line is horizontal and then they will be in the local minima, but in general they will not be. Right, so this is known as a common tangent construction. It's a pretty easy way of finding out where your equal concentrations, where your coexisting concentrations are, which then satisfy both this condition of equal osmotic pressure and equal chemical potential. All right, so we've seen that the general condition for having demixing is that we need a negative second derivative. If I look at this curve, to be precise, well, the second derivative will be negative roughly in this blue regime here. But our coexisting phases are in themselves, of course, in regions where the second derivative is positive. They're too close to local minima, and at a local minimum, the second derivative is always positive. So how does that work? Well, this has to do with the two different kinds of phase separation that you can get. If you prepare your system simply by mixing stuff together in a state that you're in this concave region, in the blue region here, where the second derivative is negative, you will always get spontaneous immediate phase separation. If you prepare your system somewhere outside, but still within the range where you can demix, right, according to the mixing criterion, then the system can demix, but you need to give it a little kick to get going. There is going to be an energy barrier before it will actually demix. This is something close to what happens if you cool down liquid water. If you do this very carefully, without any disturbance and so on, you can cool down the liquid water to several degrees below zero before it actually freezes over. And that's because of the same effect. Your system becomes what's known as metastable. You're in a local minimum, but you need a little kick to get to the global minimum. So the points on the phase diagram that we're going to get for the out of this eventually, where the system will be mixing or demixing. And so there's several options. And the simplest example, so let me write here again F and phi, is that we now make a phase diagram with temperature as one variable and this concentration as the other. And typically at very high temperatures, everything will be mixed. Everything will be happy. But then if we lower the temperature at some point, we will get demixing. So there is some critical temperature with corresponding to a critical point. And below that critical temperature, things will demix. And typically what we will get is that we will get a line and if you're inside this region, your system will demix, but not necessarily spontaneously. So this outer line is known as the binodal, indicating the region, separating the region of one phase from the region of two phases. Right? So here we have one phase. Here we have, and inside the binodal we have two phases. But then we have a second line, and the second line is, if you're inside the second line, then you will always spontaneously demix. And this line is known as the spinodal, and a typical graph will look like this. So this blue line here is the spinodal. Right? And so inside the spinodal, you're unstable, spontaneous demixing. And if you're in between the binodal and the spinodal, you're metastable. And whether you will demix or not depends, among others, on whether you get a kick. Inside the spinodal, the method of demixing is known as spinodal decomposition. It is very pretty to watch, and you can find many YouTube movies of this. If you're in the metastable region, typically your demixing happens to a process known as nucleation and growth. Right? Once you have a large enough fluctuation, nucleus of the new phase can emerge, and that will then grow over time, spreading through the system. Of course, you can have multiple of these nuclei that then also over time can merge together to make one uniform phase. How do we find these lines? Well, the spinodal is pretty easy. This is the point where you go from a positive second derivative to a negative second derivative. Of course, those are the points where the second derivative equals zero. Right? So finding the points of the spinodal is simply solving where is the second derivative equal to 0. For every temperature, we have then 2 points. And then you can do this also then as a function of temperature, and you'll get the description of the spinodal line. Finding the binodal is harder. That requires finding these points phi A and phi B, which lie on the binodal. And those points we can only find by solving these 2 equations indicated with red bars here. Equal chemical potentials and equal osmotic pressures. So spinodal is easier because you only have to solve 1 equation. That one can sometimes be done analytically. The binodal, typically you have to do numerically at least, and then process through to the phase diagram to get all the points. However, once you demix, you will always end up with concentrations on the binodal that are typically connected together by a line in the phase diagram. Right, this is the line between phi A and phi B. Right, so here I have the phi A and the phi B. Right, and this line connecting them is known as the tie line between the 2 phases. Finally, there's this point at the top, known as the critical point, that we have encountered before in phase coexistence between liquid and gases and between magnetized and unmagnetized systems. So we also have a critical point here. Obviously, at the critical point, the second derivative of the free energy will vanish because it's a point on the spinodal. But it's also where we go for the spinodal, where we go from a curve which has a single minimum to a curve which has 2 such minima. And that means that at the critical point, we also have 1 higher order derivative that vanishes. So at the critical point, we have that the second derivative of the free energy is 0, but also the third derivative of the free energy. And so finding the critical point is typically the easiest because the higher derivatives will typically give you lower order polynomial equations. And so finding the critical point is fortunately the most interesting point, but it's also fortunately typically the easiest point that you can find. All right, so this is a lot of theory about how things work. We have come a long way because we can now apply a lot of this theory to concrete examples. And in order to do that, we are going to build such a concrete example. It's known as the Flory-Huggins model for phase coexistence, which allows us to study both simple solutions where we have particles in a solution, but also to expand to polymer solutions where we have particles which are much larger than the solvent itself, the particles of the solvent itself, which will be then the topic of the next point.